Oh, AP Physics, we are going to learn some more stuff, even though from what I hear, this isn't going to be on the AP exam, but my gosh, we can't not learn this. This is good stuff. In the last video, we learned what the magnetic field was. We learned that a magnetic field, pokes, say if this is the North Pole, magnetic field pokes out of the North Pole. It pokes, by the way, into South Poles, and it tends to do a loop around like that. And we'll talk more later about magnetic fields themselves and what produces them and why they get produced. But in any case, they do pop out of North Poles. And we learned that a positive electric charge basically doesn't give a flip about a magnetic field. It's electric. And that's magnetic. So they're two different things, right? Not quite. They wouldn't have stitched electricity and magnetism together as a course if they had nothing to do with each other. I mean, they could, but they do have a lot to do with each other. So what happens is when a charge is sitting in a magnetic field, it doesn't feel it, but as soon as it starts to move with some component across the field lines, like here's the field lines, the magnetic field lines that stick out on the North Pole. Let's take this positive charge, move it to the right. There's this velocity. You learn to pull out your right hand. These are your, say it, bingers. Why bingers? Because it's called a B field for some historical reason that I've just forgotten. Magnetic field, they use the letter B. So your bingers, this is your thumb for the velocity, and your palm pushes, and that's the way the force goes. Let's see what this does. So we've got bingers pointing up. We got to contort around. Use your right hand here. Bingers pointing up, thumb this way. It gets pushed out of the board at you like that, coming at you. If it's positive charge. Now, if it was a negative charge, it'd be the other way around. You could use your left hand for a negative charge, or just use your right hand and switch the direction. So it's a surprise direction, often a third direction. We also learned that the natural thing that'll do, for instance, if you had a magnetic field that pointed into the board, the little x's mean into the board. If you had that, and you had, let's say, a positive charge moving that way, let me think, okay, bingers, thumb, up, it's going to get pushed upward. The velocity is this way, the force is this way. It'll tend to curve up. But you know what? It'll go into a circle, like an orbity looking thing. The natural motion will be a circle. The radius of the circle is easy to figure out because you can say mv squared over r, the centripetal force, equals, oh yeah, how strong is a magnetic force? What ought to be proportional to the speed? If the speed matters, it's proportional to that. It's proportional to charge. And it's proportional to the strength of the field, which is measured in Tesla, which we invented in the last video. But anyway, so QVB, and so we end up with a handy little thing that the V's cancel out. And if you wanted to figure out R, if you want to know the radius of the circle, it is algebra MV over QB. Dissecting that just a little bit, a bigger mass, all other things being equal, a bigger mass is going to be harder to turn. It's going to swing wide on the turn. A bigger speed's going to make it wider too. Now, the bigger speed does make a bigger force, but it's a lot harder with bigger speed to go in a circle, so it does make a bigger circle. Q, the bigger the charge. If the charge is really strong, it's going to get a strong force on it, go in a tighter circle. Likewise, if you got a really strong magnetic field, like a whole Tesla or something, like an MRI machine, it'll go in a small circle. Anyway, that's going to be a pretty handy thing in the applications we're about to see. Forgot one thing, QVB, sine theta, where theta is the angle between the field lines and the velocity, and see that's 90 degrees. If it's not 90 degrees, it weakens things, sine theta, so it's a little less. It also means the natural motion would have a component along the field, and it'd be a helix spiral. Not a double helix, because there's not two of them, but it'd be a helix. All right, so that's just a super fast recap of last time. This little lesson here is about all the amazing, neat tricks you can pull off doing this. So, the first thing I'll show you, first thing I'll show you is something about the frequency of the motion. Just a little mathematical thing very quickly. I had just come up with it's an mv squared over r equals QVB and all its implications. Like, for example, the R was equal to MV over QB. But look at the V. V is equal to QBR over M. QBR over M. So that's the speed you go. What about the period of your motion? Well, you know what? Since speed equals 2 pi r over t, then t equals 2 pi r, I'll do a small r, I'll keep it small, 2 pi r over v, and there's v, so, oh wait, you know what I want? I'm going to prefer to have the frequency in there. I'll show you why later. The frequency is 1 over the period, so that's v over 2 pi r. But v is q b r over m over 2 pi r. The sort of neat thing about that, I guess I'll write it as, v equals qb over 2 pi m. The neat thing about that is that r isn't in there. Silly, silly me. You see what I did wrong. You'd have caught me if this had been really class. You'd already been saying, Mr. Ernsberger, right? No. This is not the speed. Where is it? No, it's not. It's the frequency, silly me. It's the frequency. The frequency is QB over 2 pi m. Notice that R doesn't even show up in that. The frequency is determined by the charge, the magnetic field, and the mass. Hold that thought. We'll probably use that again later. In fact, I'm going to write it up in the corner in case we need it later. I think we might need it later. I'll erase the rest of the stuff. And now I'm going to get to some neat tricks. One weird trick. First trick I want to show you is actually not anything I'm going to calculate. It's just a neat trick. It's a very useful trick too. It can be a man-made thing. It can happen naturally. What if you had this? What if you had a magnetic field that's all weird and warpy looking like this? You can do that. Now we'll talk in the next chapter about how magnetic fields get made, but once they do exist, you can make them different shapes by doing stuff, Anyways, there's a magnetic field that looks like that, this B. Now this is a hard drawing to make, and I'm going to try to say it. There's a picture in the book in chapter 26 to help illustrate it. I'll describe it, I'll try to draw it, and then you can look at the picture in the book more if you didn't quite get it. What if I launched a particle, a charged particle, in this field? And now the trouble is I got to get 3D about this. Imagine I have a positive charge, and I launch it maybe this way at first, but here's the hard part. The charge is out here, and imagine this thing is got axial symmetry, so it bulges like, this here too. See that? Yep. So it's this like big old fat knot in a bunch of field lines. So if I throw it like that, okay, here we go. Fingers. I'm going to go like that. Thumb is that when it gets pushed into the board. It gets pushed into the board and a little forward, kind of. And if it gets pushed into the board, it's going to start going into the board, then it's going to have a velocity into the board, and then it's going to get pushed inward and forward. So it's going to have this inward towards the axis force, but it's also going to be sort of pushed to the right, and as I see it. So it's going to go into a circular, a spiral, a helical path, sort of a helix. But here's the thing, look when it gets over here. Now there's a component of force back the other way, and it just goes back again. And the whole point is, it can never leave. We have now trapped a charged particle in a magnetic field. Why would you want to do that? Just learn to take prisoners of charges? Heartless thing, you. Maybe you don't want it to touch anything. Maybe the neatest version of this is how you could contain something that would be otherwise dangerous. Or otherwise maybe it would be so much dangerous you just couldn't keep the stuff and mess it up. An example would be a plasma, extremely hot gases that you don't want touching the edge of a container. You can like keep them in a magnetic field and they'll never touch the sides of your machine, whatever it is. Another thing is if you're creating antimatter. Antimatter's neat. It's like where the electrons are positive and they're called positrons, and where the protons are negative and they're called antiprotons, and you make matter out of that stuff, and it's called antimatter. And if antimatter touches matter, E equals mc squared, and you figure out how much energy that is, and there's total annihilation, release of gamma rays. If I had an antimatter kilogram and a kilogram and I brought them together, I would lay waste to the entire metro Atlanta area at least, because it would be many megatons of energy released by that. So you don't want your antimatter touching the sides. Not that you have that much, but anyway, you keep it in a magnetic bottle. And I'm going to tell you the bestest magnetic bottle ever. And people didn't even make it. The Earth. The Earth's a big magnetic bottle. I'll show you why. The Earth's a magnetic bottle because it's got a magnetic field. You probably knew that. That's why they named things north and south. So the Earth's magnetic field does bulge out like that, and charged particles from the sun show up and they get trapped on the field lines. And they do this kind of business. They spiral around in the field lines, and it's not that they never leave. Sometimes they do dip into the upper atmosphere and cause the glorious, beautiful aurora borealis or australis, the northern and southern lights, as the charged particles from the sun spiral around the field lines and penetrate the upper atmosphere and energize atoms up to high energy levels for which they decay and give off spectral lines of glorious beauty. That's the aurora, but the main thing I'm saying is these are the radiation belts called the Van Allen belts. There's actually two concentrations of them. There's one at about like 4,000 miles up and another about 20,000 miles up. They used to think you can never go to the moon because you travel through the Van Allen belts. Well, they did. They just don't spend long in it. It's about maybe like getting a chest x-ray. But there are charged particles zipping around the Earth's magnetic field because it's a naturally occurring magnetic bottle. Okay, enough of that. Time to get all mathy. Now, first, I'm going to describe a device that you might not know why you'd want one. But the important thing is it forms a great component of another device you definitely want. Well, I don't know if you personally want one, but I'm glad they exist. Anyway, this device is called a velocity selector. And what is it? It consists of a combination of electric and magnetic fields. So what you'll do is you'll have, say, a plate that's positively charged here, and that's electric stuff. There's some charge Q up there. And there's a negative charge down here, and you know what that does. That makes an electric field. You know which way it points. This looks like the capacitor thing, you know, like that. Electric field, E field pointing that way. But what I'm going to do is I think I'm going to some markers. What we're going to do is we're going to take a little, equal to a positive charge, Q. It's traveling through this field E. You know what direction the force is on it. The electrical force is going to get pushed that way. So there's a little F sub E, I'll call it, for electrical force, electrostatic force on it. Points down, obviously. But I want to shoot this thing to the right. And I do kind of wish I had another color. I had a red marker in it. I don't know what I did with it. But I'm hiding this. Oh, I found it. I also want a magnetic field. Now I'm going to let you think for just a second. You got to get your right hand out. You got to think with your hands. I want you to think, what direction would you want to point a magnetic field so that you could oppose and neutralize this electrical force so the thing would feel no force at all? Think. Pause. You think? I'll tell you. Here it is. Get out your right hand. I know we need an upward force on it, so I need my palm to push up. My velocity is that way. That's my bum. and I need to push up, and look what my finger's got to do. My finger's got to point into the board. So here's my B field. My B field points into the board like that. That's B. And that will produce just what you want, a magnetic force. I'll call it F sub B. You don't know what else to call it, F sub B, pointing up. Now, it may or may not be equal to the electrical force. Could be. That's the condition I'm looking for, really, is to try to get it to be equal. Think about it. If it goes too fast, this force is QVB, and it goes too fast, it'll swing up like that, right? If it goes too slow, it's going to go down. In fact, if it doesn't move at all, it's going to go down. So I'm going to try to get the forces to balance. And the condition of forces balancing is super simple. It's when QE, that's the electric force, the electrostatic force, is equal to QVB, the magnetic force. And this perpendicular, so sine theta is 1. Oh my goodness, it don't even matter what Q is. And now I can tell you that the electric field's got to be VB, but the more interesting thing, I'd say, is to think about V. V is going to equal E over B. It is a worthwhile thing for you to try to figure out the units of E over B. You should take your newtons per coulomb and your whatever a Tesla is, maybe you should think about that, and divide them, and you better get meters per second. I strongly recommend that exercise. In any case, there's the velocity they go. Now, that's the velocity that makes it not be deflected. Now, if you think about it, if you have some kind of hole or aperture over here and another one over here, and you start spraying charges like crazy in here, they come flying into this thing, and the ones that are going too slow get bent down and crash into that. The ones that are going too fast get bent up. Only the ones that go just right, like the Goldilocks story, only the ones that go just the right speed will make it out the other side, so you have purified, the stream of charged particles, so that all of them coming out here are going the same speed. The only speed they could be going and make it through both holes is pretty much E over B. So you've selected those things. Look what doesn't matter. The charge, it doesn't matter what charge you shoot through there. Only the ones that go a certain speed are selected to go straight through. Now, why would you do that? Well, there's some more gizmos and devices you can make, and I'm getting to the good one right now. This is the bestest one ever. Super useful thing. Now that we have a velocity selector, and we can shoot things at known speed, let's use our little velocity selector. I think I'm going to put it, think for a second. Yeah. Okay, here's my little velocity selector here. Here's my little positive charge plate, my little negative charge plate. Maybe it's about this big. And I shoot. Now, how do you shoot charges? Maybe I should say something about that. Basically, if you ionize a gas, make it real hot. If it gets really, really hot, it gets so rambunctious in there, the electrons get knocked off. And so you got free electrons, but you also have free nuclei. We say ions. They probably have lots of electrons in the lower levels still on them, but they're ions. So you got a mixture of electrons flying around and ions flying around, positively charged ions, and you could have some negative ones. I'm thinking positive. So you shoot them through here, and the only ones that make it through your fancy little velocity selector, where you've got a B field maybe pointing into the board, and the E field pointing down, the only ones that make it through there are all going the same speed. So some fixed V as they come out. Now, how could they be different? They could be different in a number of ways. They could have different charges. They could. They could also have different masses. Now, as far as how much charge they have, probably they have one electron worth of charge, because usually when you ionize something, usually you just knock off the first one. That's probably enough for now. Oh, you might have doubly ionized. You might have 2 little e of charge, maybe 3. But mostly you're knocking off the 1 or maybe 2 valence electrons in the outer layers, and the rest of them are kind of snugged down safer close to the nucleus. In any case, comes zipping out. Let's see what happens if we have more magnetic field all over the place. Now, it does not have to be the same magnetic field, same strength magnetic field as in your velocity selector, but hey, why not? So let's say it's the same field B everywhere. Oh, what shape's it going to go? Well, let's see. It's now free from the electric field. The electric field's not trying to push it down anymore. It's free to get pushed up by the magnetic field. And, okay, Binger's bum up. Well, it's going to get pushed up at first, but when it starts going up, it's going to get pushed Binger's bum to the left. And when it gets going to the left, it's going to get Binger's bum down. So its natural motion is easy to understand. It is a circular path, and if you think about it closely, it's going to make a semicircle like that. And I know the radius of that thing. The radius of that thing is mv over qv. I'd already figured that out. Thing is, I know V good and well because this is a velocity selector. I got that thing tuned up. That's E over B. I know what the value is because I made it. The Q is probably either E or maybe 2E. It could be 1 or 2 elementary charges, but it's probably nothing in between because it can't be. B is known, and so actually the radius is known because I figured it out, and it's the mass. I'll just put it this way. Bigger masses going to have bigger radii. And that means they're going to land in different places. So there's a not very massive thing. And here's a really massive one. A little more massive. And it hits in a different place. And here's a less massive one that got bent harder and hit here. And you can have some kind of detector over here. And they slam into the detector, expose some sort of film or whatever the thing is. I'm not quite sure technologically what they use there. But you're going to slam things into different places depending on their mass. Now, there might be a whole different group of them where maybe the 2E's get in there, and maybe if you got twice that, they're going to go in twice as tight a circle, and they're all going to cluster here. But you know not to look at them because they're like way over here. Look, they're all spread out in a spectrum of masses. So not surprisingly, this is a mass spec. It's called a mass spectrometer. It's super duper useful because what you can do is you can take different, well, I mean, you can shoot all kinds of things through here. It could be molecules, atoms, ions. One of the things you can do is shoot all the same element through here, and then the different isotopes have different masses and land in different places. For example, uranium 235 being less massive would maybe the U-235 lands here, maybe the U-238 lands here. And you can find out how much, from how densely they hit, how much of the sample is U-235 and how much is U-238. Or carbon-14, it could be carbon-14, it could be, like there's a lot of, the carbon-12 is the usual stuff, but carbon-14, the radioactive kind, has a heavier nucleus. It goes out further. And when you see the ratio of carbon-14 and carbon-12 and something, you can make some assumptions about what they started with. You can radioactively date things. So this is good for radioactive dating. That's not a type of social interaction. Yeah, good name for one. Wow. And another career, maybe I'll start a business like that. But anyway, so you can show the spectrum of different isotopes, carbon. Oh gosh, you can do something else with it. I'm not trying to tell you how to make a bomb. No. But one of the approaches to separating, enriching uranium could be to use a mass spectrometer as a separating device. I don't think it worked that well. I think that's why they went with centrifuges. There were these different ideas about how to do that, distilling things, whatever. So that's a mass spectrometer. In fact, you could, they could take a sample of your hair and see what's in it, drugs or something. Probably a mass spec is involved. Land spaceships on Mars and try to find out what the dirt's made of. They use a mass spec. Mass spectrometer, you needed to learn that, didn't you? Now, there's one more device I want to tell about while I still got some time here. What is the other device I want to teach you about? It has the best name ever. It's called a cyclotron. I don't know why I capitalized the end, but cyclotron looks like it ought to have a lightning bolt after it. Cyclotron. Now, what is a cyclotron? What's it for? Well, first let me draw what one is. It has a couple of big parts that look like this. And the names of these parts, oh, those crazy physicists, they are called D's. D-E-E-S. D's. That's plural for a D. Because it's a D. Sorry, I didn't make it up, I swear. Anyway, you have these two D's because they look like the letter D. They're a big letter D, and one of them's a mirror image. You have these two things called D's, and you put them in a big old magnetic field. You have magnetic field all through there. Maybe it points into the board, let's say. So it's magnetic field pointing into the board everywhere. And then what you do, and why you do this, we'll say in just a minute. What you do is you charge this one up, let's say kind of positive. You charge this whole side up positive. You charge this whole side up negative. And that makes an electric field point from left to right. And then you release, say, a positive charge. You release a positive charge into this gap. And you know what it's going to do. And I'm sorry, the drawing's kind of small. But you know what it's going to do. It's going to try to go this way. It's going to try to go that way because the it's electric field. It's going to get kinetic energy as it shoots across this potential difference. It's going to get going pretty fast over here. It's going to go some speed v. And I erased it. I said I wasn't going to erase it, but I'll write it now. You know, R equals mv over qb. So it's going to go some speed v, and when it gets into this area, it's going to go around in a semicircle and come back around. Now, of course, if you leave everything the way it is, when it reaches the gap again, it's going to be told, no, don't come back, because it's going to have the field pointing that way, and the whole story's over. But no, that's not the way the story ends. What you're going to do is you're going to suddenly, at just the right time, I don't know if you're standing there with a switch or what, you're going to reverse the polarity. You're going to suddenly make this positive and that negative. And when you do that, you're going to whip across the gap again even faster. You're going to build up more energy. You're going to go real fast across the gap. Now, since R equals mv over qb, you're going to go on a wider radius turn. And when you come back around, you're going to do it again. You're going to reverse it again and give it a boost every time it crosses the gap. And so you're going to go super fast, and you're going to go an even bigger thing. And then you do it again. You keep reversing polarity at just the right time every time it comes around. And it builds up even more speed. It goes an even bigger radius. And maybe you do it like one more time. It gets going super duper fast, comes around here. And then maybe you got a little chute for it to go out. You shoot things out of it. It's a particle accelerator. It's a round, circular, compact particle accelerator. You have a linear particle accelerator where you use a series of fields to, like electric fields, I guess, to push it down to 2. You can have a gigantic particle accelerator like the superconducting super collider that spans like 2 or 3 countries in Europe, under the ground, under the farms and everything. And then, the large stupid me. I said superconducting super collider. That was going to be in Texas. And they ditched it, and they spent the money on the Human Genome Project and did the human genome. And maybe that's good too. Yeah, like biology, and I guess I like biology. I'm a biological entity. I'm thankful for the biology, so you can get me all figured out like that. So no, not the superconducting super collider. It's the Large Hadron Collider. Looking for the Higgs boson and all that weird stuff, and maybe ending the world by like causing some fracture in the fabric of space-time, crazy conspiracies and things like that. Anyway. It's a particle accelerator, shoots particles out fast. Cyclotron. But wait, who the heck is standing there flipping the switch at just the right time to do this? How are you going to pull that off? This goes back to something I wrote earlier and erased. I wonder if I can remember it. It was F equals, oh good Lord, QB, sorry. Yeah, that's it. QB over 2 pi m. And what I want to point out here is there's no r in it and there's no v in it. So I don't care how fast that thing's going. And I don't care what the radius is. There's lots of different radii. The thing goes round and round and round like that. I don't care. All I care about is its charge, which is probably one elementary charge. It's probably protons, probably what it is. Okay, so that's known. The fields makes the field constant. The mass is probably it's protons. They're all the same mass. You know what? They're all going to have the same frequency, so you don't have to sit there flipping a switch at just the right time to watch the little thing going around so fast. You just set it up to have a certain frequency. You tune it to that frequency, and it will accelerate particles. They're coming shooting out real fast. That is such a neat device. Now, there's also a thing about Thomson's measurement of Q over M for electrons. I'll let you read that yourself. Pretty neat trick. The mass spectrometer, the cyclotron. And there's a little thing about torques on current loops, and there's an interesting thing called the Hall effect. You know what? I'll let you read the other things. I'm going to talk about the Hall effect for just a second, if I can remember it right. Hall effect. Okay, so here's the deal. And a cheap look at the picture of the Hall effect real quick. The Hall effect. Oh yeah. So what you do is for the Hall effect, you have a battery here. I mean, that's not a battery, that's a resistor. And you put a battery in there. So let's put a battery here like that, and it comes around. And you take a big old piece of metal like that, and a current starts to flow. Now, if it's true that charges are positive, then positive charges will come flowing around like this and go that way. If it's true, and the positive charges will go across this thing. But what we're going to do, we're going to bury a magnetic field. We're going to stick the magnetic field into the board. Now, if it's all true, everything I've drawn is right, and these are positive charges, they're going to enter this region, and fingers, thumb, up. It's going to tend to go up through this big slab. This is a piece of metal. I'm sorry, I didn't make that point clear. This is a flat, like slab of metal. So the positive charges are going to get sent up this way, and they're going to collect up here, and this is going to get positively charged. And you're going to tend to like leave negative charge at the bottom, and you'll produce a voltage, a potential difference across here. You can measure it with a voltmeter, you know, and you'd find out that the top is charged positive, the bottom is charged negative. You could do that, and that's what would happen. If you're right that positive charges are doing the moving, what if it's not true? What if, in fact, negative charges are the ones doing the moving? If negative charges are doing the moving, they're moving the other way. They're going this way. So here comes negative charges. What happens if negative charges move across this way? I'll get out my left hand for negative charge, and I have my fingers. My fingers pointed to the board, bums this way. Uh-oh. Look what happens. The negative charges get pushed to the top, and the positive is at the bottom. And that reverses the polarity on your voltmeter there. So you know what we find out from this? We find out who's doing the charge carrying. It turns out the Hall effect can show us that the moving charge carriers are not protons. They are electrons, and so we know it that way. The Hall effect has other little uses you can read about in the book. And then there's weird things too. There's like quantum Hall effects and some neat stuff. And I'll let you read about that. But got to learn about the magnetic field and how charges behave in them and all the neat toys you can make with that. So I'll probably assign something. I'm kind of waiting to find out just what I think I can assign some stuff. I think I will. So we'll talk to you later. Bye.